Hello again, this is the next step video. This one is going to be about question 2 on paper 2 from 1995 again, and the question is in front of you on the screen. Let me just reposition it a little bit, so there you go. As usual, please do read the question, pause the video and try to do the question if you like. Obviously it's not necessary, but if you like, before the rest of the video. Okay, I will start my answer now. So, just briefly reading through the question again, we have n fence posts in a line. They are allowed to be red, white and blue, or red, white or blue, and the main rule is that no adjacent fence would have the same colour. So we define Rn as the number of possible ways for n posts if both the first and last post are red, and Sn is the number of ways if the first post is red and the last post is one of the other two colours. And the first thing we're asked to do is to explain why Rn plus 1 equals Sn. Now it seems to me, let's just make some general observations. This question is not, you'll notice, really using any knowledge from A-level maths syllabus. These questions are fairly rare, the ones that don't have any connection to the syllabus, but not so rare. You know, you will quite often get one somewhere in the paper. What else can we observe? So I'm remembering now. I did this question quite a long time ago, so it's a little bit difficult for me to remember my exact thought process when I did it. But I also set it as a task for some students, and it was interesting to observe the problems they had with it. I mean, it can be a little bit scary because it's a big wall of text, and there doesn't seem to be much to go on. But I recommend to follow a couple of principles. You know, always read the whole question to the end, even if just briefly scanning it, just to make sure you can see the set of tasks you're being set. For example, here we have explain why Rn plus 1 equals Sn. That's the first task. Then the second task is find Rn plus Sn. Then the third task is find the value of Rn plus 1 plus Rn. The fourth task is to prove a formula for Rn by induction, and then the last bit at the end, find the number of ways of painting n fence posts placed in a circle. Just looks like a minor modification or some kind of modification of the original task. So something you should notice is that the first four tasks are leading in sequence up to this formula that's given in a prominent position, Rn equals blah blah blah. So that formula is a formula for the value of Rn for any value of n. A formula for Rn. So if we go back to the first task, explain why Rn plus 1 equals Sn, I hope you can see that it would be foolish to start calculating or start finding a formula for Rn or a formula for Sn, really, because that's what we're leading to. Okay, so if I remember correctly, and I may be imagining it, some students made that mistake that maybe I can explain to you by showing on the white on the screen. So some students were taking an approach like this. Rn, let me start writing here. Rn starts with red, and actually that's also true for Sn, isn't it? Sn also starts with red, and Rn then has white or blue, because that's the rule. The next post must have a different colour from the previous post, and then, you know, a different colour, and so on. But something you might notice, oh, that's interesting, I've used an American spelling there, that's okay. Something you might notice immediately, you may or may not, is that means that if we're counting the number of ways of building these objects, so red, white, then blue. And the next one, notice, will be, if that's blue, this will be white or red. And if that's white, this will be red or blue. So let's sort of diagrammatically, red or blue, or what is the other one? White or red. Dot, dot, dot. You'll notice there's two possibilities here, and two possibilities here for each possibility there. So you're thinking it's 2 times 2 times 2. So you're thinking, oh, that's nice and simple. It's basically powers of 2. Yeah. So I only have one option on the first post, and I have two options on the second post, two options on the third post. So you're thinking, well, this is going to be easy. I can just use 2 to the power of, and then you just try and figure out the power. Is it n or n minus 2, n minus 1, and so on. But actually, this way of thinking is flawed, isn't it? I hope you can see why is it flawed. Little test for you there, if you didn't think about it before. Why is that way of reasoning flawed? Well, if we go back to the question, we remember that the definition was that Rn must have the last post red. Sn, on the other hand, must have the last post white or blue. So sorry, I'm just using this new way of presenting the screen. I hope it's okay. It just helps a little bit. So this way of thinking is flawed because we can't simply write, for example, 2 to the n minus 2 as the number for Rn, because Rn at the end must have a red at the end. So the question becomes, well, that means that this one must be white or blue. But if we just include all these possibilities, think of it like a tree. This is white, then this is red or blue. This is blue, then this is red or white. And then if this is red, you've got another tree, another branch. If this is red, this is white or blue. And if this is white, this is red or blue, and so on. Well, that's no good, because only some nodes, some branches on those trees will have either white or blue at the end. So we'll have another counting problem. And, all other things being equal, I would not criticize anyone for going down this road and maybe trying to figure out something about that tree and then blah blah blah. But actually, it's actually a very foolish thing to do. Foolish in the specific sense of what I was saying at the beginning. What I was saying at the beginning is read the whole question, check the sequence of tasks you're being asked to do. It would be foolish to try and find a formula for Rn just with no help, when clearly the fourth task is to find a particular formula for Rn by using the proof by mathematical induction method. It is conceivable, it is possible that there's an easy way to find the formula without doing what they're asking you to do. But since we have to do what they ask us to do, right, we have to explain why Rn plus 1 equals Sn, and we have to find Rn plus n, and we have to find Rn plus 1 plus Rn. Because that's the question, that's what we're getting the marks for. So it would be foolish to find a formula for Rn by other means. Now I apologise if this whole section was completely wasted for you, because you would never make such a mistake. But it seems that some students might. And, I said it was foolish, maybe that's harsh, but it connects in my mind to the problem that some students have, which is that you must remember that these questions are a kind of communication between the examiner and yourself. Yeah? The examiner is telling you certain things so that you will think certain things, and so that you will then proceed down certain paths. It's a bit like that argument about hence or otherwise. Of course we should always use hence, yeah? Unless there is some extraordinary reason. It should be like 1 in 20, 1 in 50 times that you don't use hence if the option is hence or otherwise. So in other words, follow the examiner's hints. So in this case, as far as I remember, I didn't try to find a formula for Rn or Sn, because I realized that they're asking me to make very specific observations. And actually these observations are fairly trivial. First one is, why is Rn plus 1 equal to Sn? So I'm going to, hopefully this method works well, yeah. So I'm going to pull up here my working that I wrote the first time I did this some time ago. So the first thing I did is I made a diagram like this, yeah? what is the idea of this diagram? Just so you can see clearly, you don't have to try and, it's not too abstract, you've got something physical to look at. This is what Rn actually looks like, isn't it? There's an R at the start, so each cross represents a fence post. There's an R at the end, and then there's n-2 fence posts in between. Now, as it happens, we know that this one here, let me just use a better pointer. As it happens, we know that this one here is white or blue, and this one here is also white or blue. But that's what Rn looks like. Now we also need to think about Sn. Sn, what does that look like? It looks like this on the same kind of diagram, doesn't it? R on the left. Let me just pause the video. Okay, sorry, I had a slight interruption there. So what we were saying was Sn looks like this on a diagram. R on the left, white or blue on the right. Okay, so now we're asked to consider, or what was it, to explain rather, why Rn plus 1 is equal to Sn. Well, what would a similar diagram for Rn plus 1 look like? So I've shown here. You can see Rn plus 1 would have R here, an extra red post at the end. But of course the key point is that the post before it must, according to the adjacency rule, as I've written here, the adjacency rule, this one must be white or blue. So in fact the first n posts of the Rn plus 1, well, it's not that they're the same, but there's the same number of options, aren't there? Because in both this case and this case we have the same start point and the same end point. So by definition, whatever set of whatever is the number of possible arrangements within this n-2 set of posts here, it must be the same in this case as this case. So we've avoided that problem of having to count this tree of possibilities based on, you know, the start and end points being the same. We don't have to count that, we just know that the number is the same by definition. So this must be white or blue, this must be red, and this must be red, white or blue. Okay, so it's obvious that Rn plus 1 is equal to Sn from that diagram. And I would consider that that actually constitutes a perfectly good answer. You don't really need to write anything else. Those diagrams are clear enough, combined with that little note that, you know, by adjacency rule. So in a way, it's a kind of a, do you have the confidence to sort of believe what the examiner is telling you, that there is a simple explanation? By the way, a little bit of sort of exam jargon maybe is, you know, a sentence like that, explain why this equals this. They're using the word explain because there's no calculations involved. You know, the majority of parts of questions involve doing some algebra or doing some calculus and getting to an answer. There's no algebra to be done here. It's just a question of illustrating or explaining. So that's why I think these diagrams represent a good answer. Right. The next part is to find the sum Rn plus Sn. Okay, Rn plus Sn. Well, this is, now they're using the word find. I should just emphasize that point. Find Rn plus Sn. Well, that means that now we will need to get a formula. But let's examine what Rn plus Sn would be. So here's Rn and here's Sn. Well, the only difference between them is the final post. In one case it's red and the other case it's white or blue. So if you just think for a minute what that implies, if we add all the cases where the final post is red to all the cases where the final post is either white or blue, well, that means we've got all possibilities, haven't we? Because in every case the final post must be one colour or another. It's certainly not green, is it? Because we've only got three different posts. So Rn plus Sn represents all possibilities. So the quantity Rn plus Sn represents all possibilities with the first post being red. Now, how many such possibilities are there? Well, we've already discussed this. We know that after the first post, the second post has two possibilities, white or blue. The third post has two possibilities, namely those two colours which the second post was not, and the same for the fourth and the fifth, and so on. Therefore, we have the very simple formula, which I've written here, that Sn plus Rn equals 2 to the n minus 1. So n minus 1, because the first post is red, so there's only one possibility there, but all other n minus 1 posts have two possibilities, so we just multiply them all together, 2 to the n minus 1. Okay, so we've done the first two tasks of the question. The third one is to find the value of Rn plus 1 plus Rn for all n greater than or equal to 1. Well, this is nothing at all, is it? Because what did we just say? We just said that Rn plus 1 was equal to Sn. So we can replace Rn plus 1 with Sn, and then Rn plus Sn will be equal to the thing we just calculated. So Rn plus n plus 1 plus Rn equals Sn plus Rn equals 2 to the n minus 1 for all n greater than or equal to 1. And we can just double check here. What happens if n is equal to 1? Well, then we get 2 to the 0, which is 1, which is correct because there's only one possibility if the first post is red, and there is only one post, then it's simply a single red post. If n, let's say, is 2, we get 2 to the power 2 minus 1 is 2, so we get two possibilities, which is correct because if the first post is red, then the second post must be either white or blue, so there are two possibilities, either red white or red blue. Now let's do the next task. This is the sort of centerpiece of the question. Prove by induction that Rn equals 2 to the n minus 1 plus 2 times minus 1 to the n minus 1 over 3. Okay. It certainly would be quite confusing to try and prove this without the hint. The hint here is to use mathematical induction. So we don't argue with them, we just simply do what we're told. There's a kind of a theme here, isn't there? So first of all, we state our induction hypothesis. What is the hypothesis? It's that the hypothesis for any integer value of k greater than or equal to 1 is that Rk is 2 to the k minus 1 plus 2 minus 1 to the k minus 1 over 3. And I'm going to call that function fk, just for clarity, so it's a function of k, notice, and not of anything else. Now let's check the case when k equals 1, where so the hypothesis for k equals 1 would be R1, which would be this calculates to 3 over 3, which is equal to 1, which is correct because there is one possibility with one post. We just checked that point. Okay, so what remains is to assume that hk is true for some particular k, and then deduce that hk plus 1 is also true. So if hk is true, then we have rk plus, well, no, not because of that, so because rk plus 1 equals 2 to the k minus 1, that is what we proved up here. Rn plus 1 equals 2 to the n minus 1. So we're going to need to use that relationship. So because that's true, I can write rk plus 1 equals 2 to the power k minus 1 minus f of k. If you remember, f of k was equal to rk, this function here using powers with k. So now I need to do some algebra. 2 to the k minus 1 minus fk equals 3 here. So I'm just using a dot to show you where I am. 3 times. All right. So I'm multiplying this 3 into this term here, so that I can divide everything by 3. So I get 3 times 2 to the k minus 1. So this is going here. Minus, and now I'm going to use fk. Fk being 2 to the k minus 1. Plus 2 minus 1 to the k minus 1 over 3. So 2 to the k minus 1, that's coming from there. And 2 minus 1 to the k minus 1, that's there. And then the divide by 3 as we just discussed. Okay, let me just remove those scribbles. Hopefully it works pretty easily. I could use Control Z actually, it's quicker, isn't it? Okay. And now we just need to do some tidying up and try to make that formula look like the formula for fk, or rather the formula for fk plus 1. So let's think carefully how to do it. It's not immediately obvious, but since we know what we're aiming at, it shouldn't be too hard, right? If we look at rk here, look at this formula again, 2 to the k minus 1, blah blah blah. So we need to replace this with k plus 1, so we're going to get 2 to the k. This power will change to k, and this power will also change to k. So I need 2 to the k plus 2 minus 1 to the k somehow. So how do I get that? Well, 3 2 to the k minus 1, well that's 2 2 to the k minus 1 plus 2 to the k minus 1. See, so let me just illustrate that with a little bit more detail. So that's 2 plus 1, that's the 3, and then 2 to the k minus 1. And then we've got minus 2 to the k minus 1, minus 2, minus 1 to the k minus 1. So this term 2 and this term become 2 to the k, and the other term 2 to the k minus 1 minus 2 to the k minus 1 cancels, giving us 2 to the power k. And then when we look at this term here, well that's okay, because this minus 1 here multiplies with these minus 1s here to give us plus 2 minus 1 to the k. So we get 2 times 2 to the k minus 1 plus 2 times minus 1 to the k over 3. And this is correct because if we replace k with k plus 1, we've got 2 to the k plus 1 minus 1 plus 2 minus 1 to the k plus 1 minus 1 over 3, which is exactly what we want if we look at our original formula for rk. Let me just do some undoing here. Don't know how far this undo memory goes. Okay. So we've proved that rk plus 1 is of this form, which is, and I didn't write this, but I should probably have written, equals fk plus 1. Maybe I'll do that here. Equals fk plus 1. So therefore hk, or the hypothesis for value k, implies the hypothesis for value k plus 1. Therefore h1 is true for all n greater than or equal to 1. We've got all the elements, yeah? We've got the step with k equals 1 or n equals 1, and we've got hk implies hk plus 1. So hn is true for all n greater than or equal to 1. Right, the last part of the question, where have I gone? The last part of the question says find the number of ways of painting n fence posts. Now in this case n is bigger than or equal to 3, but placed in a circle using 3 different colours, the same, so it's the same as before, red, white, blue, in such a way that no adjacent fence posts have the same colour. So almost the same problem. The only difference is we're talking about a circle, not a line. So how can we use the idea of a circle instead of a line? Let's think about that. You'd use some rough paper up here. So a circle instead of a line. So we had before something like this, r and dot 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 and whatever. Yeah? So let's suppose, to be concrete, that we have n fence posts here. Well, the corresponding case for a circle would be the same as this, except let's consider the last fence post in this line. Let's suppose we want to make this line into a circle by bending it round. Well, if the last fence post is red, I can't bend this round to meet this one because red is not allowed to be adjacent to red. So I can make a circle from any given line as long as the final fence post is different from the first one. So in this case the final fence post would have to be white or blue, and this would make a circle of n plus 1 posts, wouldn't it? Oh, no, sorry, that's a circle of n posts, yeah. Now we've already discussed this case, haven't we? This is the case Sn. If we go back to our original diagrams, This is the case Sn. And we know, sorry, do we know the value of Sn? I've forgotten. We've calculated Rn. We know that the first thing we proved, wasn't it, that Rn plus 1 equals Sn, that's it. Rn plus 1 equals Sn. So this was Rn, and we have a formula for Rn, and so if we want to know the value of Sn, excuse me, Sn is Rn plus 1. Now Rn plus 1 can be calculated using the formula that we proved by induction. The formula we proved by induction was that Rn, where's it gone? Oh well, let's just use the question. Oh, there it is there. Rn, just looking for the clear statement of Rn. Let's use the question paper. So Rn is this. So if we want to know Rn plus 1, well, we just substitute n plus 1 here. So we get 2 to the n plus 2 times minus 1 to the n over 3. So 2 to the n plus 2 times minus 1 to the n over 3. Okay, now have we finished the problem? They were asking us for all the number of circular arrangements of n posts. Well, not quite. Do you see the problem? Actually, it's a funny little puzzle. Why is this not the final answer? Not equal to number of circular arrangements of n posts. The simple answer is that Rn and Sn, remember, were only if the first post was red. The first post can be either white or blue, of course. And then by symmetry we could define the same quantities. Obviously there's nothing special about any one of these colours, so answer is actually 3 times the answer we just got, which is 2 to the n plus 2 times minus 1 to the power n. And by the way, let me just make a quick note. I didn't mention the fact that n was greater than or equal to 3. Let me just quickly think about that. If n is 2, well, first, it's not much of a circle with n equals 2, but if n equals 2, the formula that we calculated apparently gives the right answer. If n equals 2, yeah, I guess the problem with n equals 2 is, yeah, the relationship, it doesn't make sense, does it? Okay, I'll let you think about that. It's a small detail and you don't actually have to do anything about it. So for n greater than or equal to 3, it is certainly true that the answer is 2 to the n plus 2 times minus 1 to the n. Yeah, if n equals 1, then this gives 0, doesn't it? And if n equals 2, then it gives a... If n equals 2, I get 4, I get 6. Yeah. Okay, so actually the formula's giving a sensible answer. It's just that it doesn't really make sense as a circle, I guess. Fair enough. Anyway, I hope you found that question interesting. I certainly did. I like that question a lot because it has no connection to the normal syllabus. It has no connection to the normal syllabus, so it does require you to think independently, and it does prove something quite neat. Although I suppose you're given the actual formula to prove, so it's not amazing. It's not an amazing mathematical achievement. Somebody still had to come up with this formula here, but it's really not that difficult as long as you can take that first step. I think maybe the critical point is drawing the drawing the diagram so you can clearly understand the logic of the situation, then it's not so hard, I suppose. Anyway, I hope you found that useful. I will leave it there. Thank you very much.